Okay, so I decided to do 1.4 for my lesson. I have 1.5 already as a video that's analyzing graphs of functions and functions. So that's already in the classroom. The first few things or sections in chapter 1 are fairly review, but everybody always struggles with functions. So I figured that this would be a good additional video to make. So we'll just get going. Oh, let's see who joined. This is someone else. David joined. Okay. Okay, so 1.4 covers 4 things essentially. Determining whether relations between two variables are functions and using function notation, finding domains of functions, using functions to model and solve real-life problems, and then evaluating difference quotients. And this difference quotient thing, that is a skill that you need in calculus. So we're not actually doing calculus, but we are doing something that you will have to do in calculus to that. I mean, it's not considered calculus, but interpreting what it is when you get to calculus, you'll see how that connects. So you do difference quotients a lot in calculus, but those are in terms of something called a limit, which is something we won't talk about till week 8. So we're just kind of learning how to do the algebra behind it before you actually learn the calculus behind it. So I'm going to just start from the very beginning, definition of a function. So a function is a relationship between two variables where each input or independent variable has exactly one output or value, and that output is considered the dependent variable. So I have the definition from the textbook here. They define it in terms of sets. So your input is considered set A, your output is set B. And so you have everything in the input goes to one output, one element in Y. The set A is the domain, and then B is the range. Now, there are some characteristics of a function. This goes a little bit beyond what you have seen in college algebra. So we know that A is the input, and then B is the output. So each element in A has to be matched with an element in B. But B does not get matched in A to be a function. Or some things in B may not be matched. So it's okay if you don't match to everything in B, but everything in A has to go somewhere. So what this means is if I have, I just have a series of numbers, whatever those numbers are, everything in A has to go somewhere. Whoops, I did not draw a function. Each thing in A goes to something in B, but it doesn't have to go to everything in B. So you could have things in the output that don't have a number that go with it, and that's okay. And you could have two elements in A going to the same thing in B. That's what I tried to draw here. Let me try a better job. So it's okay if your input goes to the same output. You just can't have more than one output. So this is another way of restating different ways you can interpret whether something is a function. These characteristics could be helpful if you try to determine something as a function, because you can just go through and think these as check boxes. And if you can check off each of these characteristics, then you know what you have as a function. But it all goes back to you have inputs and they can only go to one output. And that's the basic rule. And then these are just kind of consequences of that rule. So we're going to look at functions in two different ways. We've got a table, and then I have a set of ordered pairs. And so the question is, let's start with the table. Does the following table represent a function? So ask yourself, does every input only have one output value? So I'm going to ask you guys that. Does every input only have one output? David, you can type it in the chat box if you want. or you can turn on your microphone, whatever you'd like.
Yes. Each input only has one output.
Correct. Yes. So, sorry, I've got to get my thing back up. So, yes. So that means that, yes, this is, oops, if I have my pen, this is a function. So even though the output is exactly the same, it doesn't matter because just as long as each input has only one output with it. Now, what about our set of ordered pairs here? And it doesn't matter that some are letters or some are numbers. In an ordered pair, the first number is the input, the second, I shouldn't say first number, the first spot, because these are letters, the first spot is the input, the second spot is the output. So do we have each input only having one output associated with it in our set, our list of ordered pairs here? What do you guys think? Okay, let's see. I have somebody type. And Joanna says no. Go ahead, continue, Joanna. I see you're also typing. Maybe it's fooling me. Sometimes this says people are typing and then they're not actually typing. Not typing. Okay, I figured I'm like, oh, maybe it's one of those. Yeah, you are correct. So the second one is not a function, and that is because we have C. C is an input twice, and when it's listed twice, it has two different outputs with it. It has 2 and it has 3. So our input of C has 2 outputs with it, and so this is not a function. Now, when we look at equations here, this is a lot harder because you don't have a set of numbers, and so I recommend if you're trying to determine if an equation is a function is to graph it. And so my favorite place to graph is Desmos. So I am going up Desmos. And I'm going to try to, oh, it always likes to get bigger. I want to make sure that I can have it there so we can also see the equation. Okay, so the first one is x squared minus y equals 0. Okay, so this gives us a parabola, and I can zoom out here. Even though it's not written in our normal form for a quadratic, we are getting a quadratic out here. And so when we're looking at a graph, we're looking at the vertical line test. Basically, if you draw a vertical line anywhere, is it going to hit your graph twice? And in this case, no. No matter where we draw a vertical line, I'm only going to hit that red parabola once. So this x squared minus y equals 0, that is a function. Now I'm going to look at the other one, y equals, and to get the square roots, I'm going to, there, I got my square root button, x plus 5. Okay. So here, I'm going to zoom out. So again, no matter where I draw a vertical line, I'm not going to hit the graph more than once. I'm going to hit the blue graph only once. So this one is also a function. So both of these equations represent functions. The general rule, if you're looking at an equation, is that if the y has an even exponent, it's generally not a function. If the y has an odd exponent or no exponent, it's a function. So that's just a general rule. And we can test that rule if I changed, instead of just being y, if I wrote y squared, all of a sudden that's no longer a function because now we have it on both ends. And that's just if it's an even. So if I made that y to the 4th, it's still, with the vertical line test, it violates the vertical line test, and so that's not a function. So that's a nice little rule if you're trying to determine if something is a function. Same thing here with this first one. If I, normally, right now I have no exponent on the y, but if I add an exponent and I add an even exponent, all of a sudden it's no longer a function because now it's the y we would, if we had a vertical line, we'd go through it twice. So that's the way to determine if something is a function, just by looking at what is going on with the y. It doesn't really matter so much with the x, it's the y that matters when we determine with functions, because we're looking, can we get more than one y value out? And so that's why we look at the y to determine if it's a function or not. So I'm going to draw both of these pictures on my slide. So here we got a parabola. So this is a function. And then the other one, when we drew that, we got something that looks like that, and that is also a function. And then if you have an even exponent on the y, generally means not a function. Oops, let me spell that correctly. Generally means not a function. Do you guys have any questions on that? Okay, so I'm moving on. Function notation. So function notation, a lot of people struggle with. That's where you have f of x. So it's the same thing as y. Wherever you see that notation, just tell yourself this is y. So f is the name of the function. So we usually use f just because that stands for function, but it could be anything. Y is the dependent variable, the output. And what's in parentheses x, that's our input variable. And then f of x is the value of the function at x. Basically, if you see f of x, that's, you want to think that it is considered the value of the function. The value of the function is always, we always think of that as y. So if you see anything saying find the value of the function, you're finding the y value that matches with the x. And so then you plug in whatever your x value is, get the output, that is your function value. So that's what we think about here when we have function notation, is finding the function value is your output value. So here, so you may have noticed the language is changing a little differently. If you took college algebra here at Grantham, I know many of you have just come from college algebra, so you may have noticed that we didn't really use the language find the function value. You know, we're kind of getting into a little, as we move up in the math classes, you get into more mathy language, and so now instead of just saying find h of 2 or whatever, we'll say find the function value. So then you have to know, oh, this is new vocabulary. What does the function value mean? I'm finding the output when I plug in my input. So we have h of t equals negative t squared plus t plus 1. And we're finding the function value, the output. So this means I plug in my input and then see what I get out. So we start with h of 2. So that means my input is 2. So everywhere I see t, I'm going to replace that with 2. So I have negative 2 squared plus 2 plus 1. And then I want to simplify that as much as possible. So I'm going to just move to the right here. 2 squared is 4, so I have a negative 4. And then I can also add 2 plus 1, which is 3. So I have negative 4 plus 3, and that gives me negative 1. So my function value is negative 1, or basically the y value that goes with 2. Next one, h of negative 1. So you want to be very careful when you plug this in, because we have a negative t squared, and then we're putting negative 1 in for t. So you basically have two negative signs here, and then you also have your exponent. Then plus negative 1 plus 1. So we're following the order of operations to simplify. When you have functions, you just work on the right side. You never touch the left side. So that's why I'm moving all the way to the right here, because we're not solving for h. We're just evaluating the right side. So we have a -1 squared. So that's -1 times -1. So we got a positive 1, but then I have a negative sign in front of that. So I'm actually going to get a -1 there. And then -1 plus 1 is 0. So I just have -1 plus 0, which gives me the same answer, -1. Now the last one here, we're not plugging in just a number. We have x plus 1. So we're following the same rule. Everywhere we see t, I need to replace it with x plus 1. So I have a negative, and then x plus 1 squared plus x plus 1, and then plus 1. But we want to simplify this. So this is where we start using algebra. We're going to have to take that x plus 1 squared. We need to multiply that out. And I have the room here, so I'm actually going to work down. So first I have that negative, and then I need to multiply x plus 1 squared. So I'm not going to show that step. If you, on your own time, if you need to double check that on your own, you can double check that multiplying. But this gives us x squared plus 2x plus 1. And then I have plus x plus 1 plus 1. Now I need to distribute my negative sign. So I get negative x squared, negative 2x, negative 1, plus x. And then I'm going to add the 1 plus 1, so that gives me 2. And now I am going to move to the right because I'm running out of room here. So now I want to combine my like terms. So I have a negative x squared. Now I'm looking at the x's. I have a negative 2x plus x. So negative 2 plus 1 is -1, so that gives me negative x. And then I have a -1 plus 2, which gives me a positive 1. And so our function value here is not a single number, it's an expression. It's negative x squared minus x plus 1. So before I move on, do you guys have any questions here? Yeah, Joanna. Okay. Not a problem. For the first example, how do I know when the first number will be positive or negative? That is a good question. It all depends on where the parentheses are. So I plugged in a positive number here for t. If you plug in a positive, I don't need any parentheses. That exponent 2 is just on the 2. So I'm just squaring the 2, not the negative. So that negative is not involved in the squaring, and that's why I got a -4, because it's not -2 times -2. It's a negative, then 2 times 2. And this is reinforced when we look here that negative is not in parentheses, so that exponent only applies to whatever t is. Now in the second example, I'm plugging in a negative. So whenever we plug in a negative, we have to have parentheses. So now I have parentheses, so I'm squaring a negative. And whenever you square a negative, you always end up with a positive. So I would get a positive 1 out there, but then I have this second negative sign that turns it into a negative 1. So that's how that one also became negative, even though we plugged in a negative number. Does that help answer your question? Perfect. I actually just went over positive and negatives with exponents in my 104 class, and so that video will be on YouTube probably by tomorrow morning. So if you need review of that, if you're subscribed to my YouTube and get notifications, that might pop up. So you may want to, it doesn't hurt to get some review of that. Yes, David, you have a question. Yes, h of t is the same thing as f of x. So here our function is called h, and the t is just telling us that our input variable is t instead of x. So it's the same, it's function notation, even though the letters are completely different, you want to look at the pattern of how they're written. So I could use anything, and when we plugged in x plus 1, what we were doing is switching variables, switching from t to x in a way. Yes, so after we did h of x plus 1, our output y is equal to negative x squared minus x plus 1. So yes, this is a function. Because we have only one y, it's okay to have more than one x, and if we were to solve this, set it equal to 0, we could get two x values. But we only have one y, so it's a function. And whenever we use this function notation, this h of t, no matter what you plug in, you're always going to get a function out. So there's no way to put something in for t and not have a function come out, because once you can put it in function notation, it's always going to be a function no matter what number, what letters, or whatever you plug in. That's great questions. Are there other questions? Okay. Now I'm working with function notation again here. These are different types of questions that you may encounter. So here, for example 4, we have find all real values of x for which f of x is equal to 0. This is another way of asking for the zeros of a function. So there are lots of ways to ask for the same thing, but you can ask them in different ways. So the 0 of a function is also the x-intercept of a function. And 0 is when y is equal to 0, but in this case y is f of x. So we have f of x equal to 0. So when it says find all real values of x, that means if you get an imaginary number, you ignore it, because we want only real numbers. So to solve this, you set each equation equal, so I'm still in the highlight. That's no good. You set each equation equal to 0. So for the first one here, f of x equals 4x plus 6. I replace f of x with 0, so I get 0 equals 4x plus 6. And then I solve. So I want you guys to solve this one and tell me what x is equal to. When you get your answer for x, you can type that into the chat box. Okay, so David, you have negative 1.5. How would we write that as a fraction? Because we want to, in algebra, and even when you get to calculus, most of the time, we're going to keep things in fraction form. Okay, so negative 1.5. And how would we write that as an improper fraction? You will find when you get to calculus that improper fractions are much easier to work with than mixed numbers. Negative 3/2. Perfect, William. Great teamwork. So to solve it, we subtract 6 from both sides, and then you would divide by 4. So you would end up with negative 6 over 4, which then you would reduce, because you can divide both the top and the bottom by 2, and we get negative 3 over 2. And as long as it's not an imaginary number, that is your answer. So we want to keep things in fractions whenever possible and improper fractions whenever possible, because it will make your life easier when you get to calculus. So it's just good to get in that practice now. Now the second example here, f of x equals 12 minus x squared over 8. So I'm going to do this one because this one is a little interesting. So you replace f of x with 0. So you have 12 minus x squared over 8. So I always, whenever I'm solving, I want to eliminate fractions. So I am going to multiply both sides by the denominator. So I'm going to multiply, oops, let me make sure I change colors here. Both sides by 8. So 8 times 0 is 0. And then I've eliminated my fraction, so I get 12 minus x squared. So the denominator in this case doesn't matter when we're trying to find where this is equal to 0. So I like to have a positive x squared. So I'm going to add x squareds to both sides, which will give me an x squared equals 12. And now I'm solving for x. And so to do that, we take the square root of both sides. And we want to not write this decimal. We want to leave it in radical form. So I have x equals, and whenever you take the square root and you're solving for x, you get a positive and a negative answer. And then we have the square root of 12, which reduces to 2 square root of 3. Now, if you're wondering how I got 2 square root of 3, I'm going to just go on the top right here. So square root of 12, I can split this up as the square root of 4 times 3. And I can then split that up as square root of 4 times the square root of 3. Then I can take the square root of 4, which is 2, and that gives us 2 square root of 3. So when you get something with square roots, you don't want to actually get the decimal version. We want to write the exact version, and then if it has a radical in it, we want to try to reduce it whenever possible. Are there any questions on these two problems for example 4? Okay. Example 5. Find all real values of x for which f of x is equal to g of x. So if f of x is equal to g of x, and I have f of x equaling square root of x minus 4 equals g of x, which is 2 minus x, that means I need to set the two equations equal to each other. So I have the square root of x minus 4 equals 2 minus x. And now we need to solve for x. Now, if you took college algebra at Grantham, this goes back to week 3 where we're solving radical equations. I know some people go into pre-calc and don't have to take college algebra, so maybe you don't remember how to do this. That's why I chose this example. So I get the square root by itself. So to do that, I'm going to add 4 to both sides. So that gives me the square root of x equals 6 minus x. Now to get rid of something that's square rooted, you square it. So that means I want to square both sides. And when you square both sides, that's where you have to worry about getting extreme solutions. You might get numbers that are not actually solutions. You can get extra solutions that don't work. Because we started with something that has an x inside the square root, we should get one solution to this. Now when I square it, I'm going to end up with 2. So I know that one of those solutions is not going to be a real solution to the original problem, and I will have to check to see which one is the solution. So when I square a square root, those cancel, so I just have x. And then I need to FOIL out 6 minus x. So I have minus x times 6 minus x. So I'm not going to show that step, but you can do that on your own on paper. That will give you 36 minus 12x plus x squared. So now I have a quadratic equation, and to solve a quadratic equation, you need it equal to 0. So I need to subtract the x on the left so that I have one side equal to 0. So I have 0 equals, and I'm going to rearrange this so that I have my x squared first, then I have minus 13x, and then I have plus 36. So I just flip-flopped my x squared and my 36 so that it's in the order that you usually see quadratic equations. Now I'm going to move over. And now when we solve a quadratic, we have lots of options. We can factor if it's factorable. You can do completing the square, which is really annoying, and I don't ever recommend doing that. Or you can use the quadratic formula. And this is just a bonus fact, but just a few days ago, I read an article that a new way to solve quadratic equations has been found that's supposed to be easier than the quadratic formula. So I have not yet looked into what the method is, but I plan to. And if it is easier, I'm going to start teaching that method. So something new has been discovered about quadratic equations just recently. So going to our quadratic equation, since I don't yet know what that method is, I'm going to choose between factoring and the quadratic formula. And this particular problem can be factored. So I have my 0 equals, and I'm going to have my x and my x. And I'm looking for two numbers that multiply to 36. And if I'm adding to a negative, they both need to be negative numbers, and they're adding to a negative 13. So 9 times 4 gives me 36, and 9 plus 4 is 13. So if I make these both negative, that will factor the way that I want. And so then I'm solving for x. We set each factor equal to 0. and then you solve. And I know that this is going to end up giving me x equals 9 and x equals 4. Basically, the signs get flipped. So now I know that one of these is not going to be an answer. I have an extra solution here. I should only get one solution because I had only x underneath the square root. So one of these is a wrong answer. So I have to check them in the original problem. So I'm going to do this in a different color. And so I'm checking them in x, square root of x minus 4 equals 2 minus x. That's where you want to check the answer. So I'm going to plug it in. So I've got square root of, we'll start with 9 minus 4 equals 2 minus 9. So the square root of 9 is 3. And then I have 2 minus 9. So 3 minus 4 is negative 1. 2 minus 9 is negative 7. Okay. That definitely did not work. Because those don't match. Now let's try my x equals 4. So I have square root of 4 minus 4 equals 2 minus 4. So square root of 4 is 2. So I have 2 minus 4 equals 2 minus 4. Well, that's going to give me negative 2 equals negative 2. So I got my left side, when I checked x equals 4, that gave me a true statement. So x equals 9 didn't actually work. So there's only one answer that makes this work, and that is 4, because that's the only one that came out true when I plugged it back into our original statement. Are there any questions? Okay. All right, so now moving on, there are different ways to represent a function. So generally, in previous algebra classes, you've seen functions written in graphs or in equations, and you've seen them sometimes in table form. One thing that you may not have seen too often was writing a function verbally. In pre-calculus, we're going to be doing a lot more word problems, and so you're going to see this more often. You're going to see functions written in verbal form. So that's basically a sentence that describes how the input variable is related to the output variable. Otherwise, numerically is just a table or a list of ordered pairs. Graphically would be a picture. You can have a graph, and then algebraically is with an equation. Okay, so now let's talk about domain of a function. So the domain is the set of inputs for the function, inputs that we're allowed to plug in and get an output, an answer. So if you have a number and it's in the domain, then we say that f is defined at x because we can get an answer out. If you plug in a number for x and you don't get an answer, if you get undefined, it doesn't work, that means it's not in the domain. So if something is not in the domain, then your y value, your function value, your f value would be undefined. So basically with domains, we exclude any values that cause division by 0 because dividing by 0 is undefined. And we exclude any values that would cause you to take an even root of a negative, such as square root of negative. Because our domain, we want to be real numbers, so if you get imaginary numbers, that's not part of the domain. So when we have equations, our domain is assumed to be all real numbers except any that cause division by 0 or any that cause us to get imaginary numbers. Those are the only two parts of the domain of an equation that we don't allow. So I have two examples here. So first one, I have g of x equals 1 minus 2x. So we're not dividing by anything here, so we don't have to worry about division by 0. And we don't have any square roots or any fourth roots or anything like that, so we don't have to worry about the imaginary exclusion. So that means our domain is going to be all real numbers. So you're just checking, am I dividing by 0 anywhere? Do I have a square root anywhere? If not, my domain is automatically all real numbers. So nice and easy. We assume all real numbers unless there's something that will tell us it's otherwise. Second example, I have h of x equals 6 over x squared minus 4x. So here we're dividing. So now I do have to worry about my domain, because now I have to worry about, am I dividing by 0 somewhere? So we're going to have all real numbers except wherever we divide by 0. So we need to look at our denominator to find out where our denominator is equal to 0. So we have x squared minus 4x, and I don't want that equal to 0, so I'm going to just write does not equal 0. And I want to find what values make this 0, and I can treat it the same as solving a quadratic equation with equal to 0 with the not equal. It's the same sort of steps. So I have a quadratic, so I want to factor. Because I have an x squared and an x, I can factor out an x, which gives me x minus 4. So that can't give me 0. So normally when you solve a quadratic, you set these equal to 0. Well, we're setting them not equal to 0. So we get that x cannot equal 0. That comes from the x. And then the x minus 4 part, well, that tells you x minus 4 cannot equal 0. And when you add 4 to both sides, that tells you x cannot equal 4. So our domain for this case would be all real numbers except 0 and 4. So you can write it that way. Sometimes it will be written in a set to indicate that it's any x as long as x does not equal 0 or 4. Or you could write it in interval notation. Interval notation is very clunky for domain. So we can go from negative infinity to 0, and then we can go from 0 to 4, and then we can go from 4 to infinity, but we can't include 0 or 4. So interval notation is really gross. I generally will either write all real numbers except, or I will write it in set builder notation for domain, because it's pretty simple. We assume all real numbers, and then we just say, well, what are we excluding? We're saying x cannot equal 0 or 4. Are there any questions? Okay. Okay, now example 7 here. Find the domain of f of x equals the square root of x plus 6 over 6 plus x. So we've got two things. When we look at domain, we assume it's all real numbers, except if we're dividing by 0 or there's a square root. We have both cases here. So we have to think about both of those things as far as our domain. So I'm going to start with the denominator dividing by 0, because we just did an example like that. So to find out what is excluded, I'm going to do the same thing I did, where I'm going to say that our denominator, 6 plus x, that cannot equal 0, because if it does, we have a problem. So if you're solving for x, you can subtract 6 from both sides. You get that x cannot equal negative 6. Now we want to consider the square root. So we don't want imaginary numbers. So that means we can't have negatives inside the square root. So underneath the square root is x plus 6. And so that has to be greater than or equal to 0. I'm going to highlight these because I don't want you to get confused about where these are coming from. So inside the square root, it can be equal to 0. That's completely fine. Or it can be greater than 0. It can be positive. It just can't be equal to negatives. So I'm going to solve this inequality. I'm subtracting 6 from both sides, and so I get that, whoops, x has to be greater than or equal to negative 6. But we also know that x cannot equal negative 6. So when we put these two things together, x is not 6, and it has to be greater than or equal to negative 6. I think I said x is not 6. X is not negative 6. X has to be greater than negative 6 because it can't be equal to negative 6. So that equal to part for greater than or equal to part, that would kind of contradict each other. So I have to be greater than negative 6 when I think of those together. So you can say your domain is all real numbers where x is greater than negative 6. Or if you want to write this as a set, you can say, okay, any number that I plug in, it has to be greater than negative 6. Or if you want interval notation, that would be negative 6 to infinity. Now, if you're having trouble thinking about, well, how did I know that it was greater than negative 6? We can think of this as a number line. So I'm actually going to use this lovely line here as my number line and put 0. And I'm going to put negative 6 here. So I know that I cannot be equal to negative 6. So I'm going to just put a circle, and I'm going to just put this above here. And then I know that I need to be greater than or equal to negative 6, would be a closed circle, and then everything to the right. I have two different kind of rules here when I'm looking at the domain on my number line. When you are considering domain, you're looking for the intersection. You're looking for what do they have in common. And so if I were to think about this not equal to 6, that means I could have everything to the right, or I could have everything to the left. I just can't have x equal to negative 6. So this would be graphically represent x does not equal negative 6, and while the line on top graphically represents x greater than or equal to negative 6. So if you're looking at your solution for the domain, you want to look at where are those two pictures overlapping. Well, they are overlapping here. They both have that arrow going from negative 6 on, but they're not overlapping at negative 6 because one has a closed circle and one has an open circle. So that's why we have the parenthesis there, because since it's not overlapping, negative 6 is not included. Are there any questions? Okay. Now this example is a word problem. It's an application. This is an odd from the textbook, and I'm going to zoom in here so you can read it a little better. I chose this particular problem because volume of open boxes is a type of problem that shows up in calculus all the time. So I believe that pretty much everybody who has to take pre-calculus is taking it because you have to go on to calculus. So I wanted to pick this problem because this is something that you see when you go on to calculus. So we have an open box of maximum volume made from a square piece of material 24 centimeters on a side by cutting equal squares from the corners and turning up the sides. And so they have this picture. You're cutting out squares of size X, and when you cut those out, then you're left with these little flaps that you can fold up. So that's sort of this picture, and when you get to calculus and you have problems with this, you have to draw that picture all the time. So here we have a table. The table shows the volumes in cubic centimeters of the box for various different heights. Use the table to estimate the maximum volume. So when you're estimating, there's not really a right or wrong answer. I mean, you can be way off and that could be considered wrong, but as long as you're in the ballpark, then, that's considered an estimate. So when you guys look at this table and you're looking at these numbers, what estimates do you guys come up for the maximum volume, basically? So what do you think the maximum might be? You guys can just type it into the chat box based off of that table. Okay, so Mark, you say 1024. William also says 1024. Anybody else have any other estimates? Oh, David says 2048. Interesting. I mean, obviously we know it has to be at least 1024 because that's the maximum number we're seeing here. I would say that probably most people would guess 1024 because that's the highest number you see in the table. If you wanted to think outside of the box, you can go like David did and double it and think, okay, maybe we go that high. When I look at this, I see that if I say 1024 is the maximum, to the left and the right of it, it's not a mirror image because I'm 972 on one side and 980 on the other side. So I would say, oh, maybe it's actually higher than 1024. It's not perfectly symmetrical. So I might say like 1030 or something like that. It's just an estimate. Now, when you guys are doing an application assignment and it says to estimate the maximum volume or estimate something, you don't want to just give a number. You want to explain how you came up with that number. So if you say 1024, you say, I estimated at 1024 because that's the highest number I see in the table. Or David, you can explain, I estimated at 2048 because you can type that in. Or if you did some math formula, if you maybe did some multiplication or something, you would show that work to get the estimate. I picked this one not only because it's good for showing you something you have to do in calculus, but also because there is a problem on the application assignment where you have to do estimates. And so when you have an estimate, you need to kind of back up how you got that estimate. You need to kind of show your work. So that's why I wanted to go through here. So those are great estimates. Those are totally fine estimates. Because this is an odd, the book does have an answer, but it doesn't really matter as long as you can back up your estimation. Now, part B says to plot the points from the table in part A. So I'm going to bring back up Desmos here. And you can insert a table into Desmos. I can do add item and table. So I'm going to just kind of, oops, I lost it. I wanted to, okay, so my X values just go 1, 2, 3, 4, 5, 6. And then I have 484, 800, 972, 1024, 980, 864. Whoops, 864. Okay, now you can see that I don't actually see that on my graph here. But if you scroll, there's this plus sign. If you hit that, that will zoom to your pictures. So, okay, so part B says just to plot the points. Okay, so now, second part, does the relation defined by the ordered pairs represent a function? So, is this a function, guys and girls? Okay, Mark, you say yes. Why is it a function? Or if anybody else has a reason why it's a function. How do you know it's a function? Okay, David says you're not sure it is. So one of the things about pre-calculus is you get these word problems, and you want to make sure you're explaining your thinking. So when you get a question that's just a yes or no question, you don't want to just say yes or no. You want to explain why you came up or how you came up with your solution. Because that will help you get maximum points, and because there are these journal entries that, so you want to explain your problem solving process, you want to think about how did you come up with these. So Mikhail, you said use the vertical line test. That's a great option. So if we use the vertical line test, if I draw a vertical line through any of the x's, I only get one output. There's only one y value coming up. So, and Mark, you say x equals 1b. I'm assuming that's sort of that you're trying to say the same thing. There's only one output there. You probably accidentally typed b instead of b. Yeah. So that's like when you're working on your application assignment and there's a question where, is this a function, yes or no? You can say yes, because when I do the vertical line test, it goes through one spot. Now, if you're looking this horizontally, it might be like, oh wait, but there's two values that look to be at the same y value. That's fine, because we don't really care if there's more than one y value. We care, is there only one x on this graph? So based off of what we see, yes, this is a function. Now, part C, oh, and William, you're typing. Do you have a question or anything to add? No? Okay. One of those words probably fooling me. So part C says, given that v is a function of f, so now like the second part, they're like, oh, now they're telling you, yes, this is a function. Write the function and determine the domain. So writing the function, so this is where you're getting your problem solving skills. So I'm going to go back to the slide. So we're writing a volume. So volume is length times width times height. So I'm going to have to zoom out so I can actually write here. Okay. So I'm going to get my pen out. Volume is length times width times height. And this is the step that you often have to do in calculus, except that when you get to calculus, you do a lot more than we're doing here. So the length, when you're looking at this picture, the length is labeled here at 24 minus 2x. And it says that this is coming from a square, so that means the width is going to be the same. The width is also going to be 24 minus 2x. So I'm going to write this as a function of x. I'm going to write v of x. My length is 24 minus 2x. My width is 24 minus 2x. And then the height is x. You can see that the parts that we folded over, that forms the height, and so we get x. So now we have written this function for volume in terms of x. And so then the question says determine the domain. So let's look at the domain rules that we just talked about. We assume the domain is all real numbers except if you were dividing by 0 or you have a square root or like a fourth root or something in there, and then you have to worry about exceptions. So knowing those rules, what would be the domain here? You can start by asking yourself, do we have any division in our equation here? I don't see any division. Now you say, do we have any square roots? I don't see any square roots. So because we don't have any division, we don't have any square roots, our domain here is going to be all real numbers. So domain is all real numbers. And that's just for the equation. So I'm going to just write, that's the domain of the equation. Now, if you think about this as a real situation in terms of volume, x represents a height of this box we're forming. Well, we can't have negative height. So we could say, okay, our domain would really be x has to be greater than 0 if we're considering the situation itself, the real life situation, because we can't have negative heights. That would not make any sense. So there's a difference between asking for the domain of the equation or the function, which is what part C asks for. So C specifically says, right, it's talking about the function and its domain. So for C, your answer would be all real numbers. But if somebody was asking about the domain and it didn't specify the equation or the function, then you would say, well, in this situation, the domain would have to be x greater than 0 since we can't have negative values. That wouldn't make any sense. Now, the question doesn't say the problem doesn't say anything about graphing that equation, but I figure let's graph it because, oops, why not? Oops, wrong thing again. Why not? We have it. We figured it out. So I'm going to just type in v of x equals 24 minus 2x, 24 minus 2x, and x. So you can see it forms the graph, and it's interesting because since x is in there 3 times, it's actually a cubic. So if you look at this, you're like, oh, if you were looking at the graph and you were asked what the maximum is, well, theoretically, the maximum is infinity because it goes up forever. But realistically, in this problem, and this goes beyond what the question is asking, but realistically, our domain, you only care about the parts probably from 0 to that 12 or something like that. Because the piece of paper starts, we have the material, the square is 24 centimeters on a side. So you can't cut off half of 12 is or half of 24 is 12. So you can't really have an x that's larger than 12, or you have some problems when you're cutting that paper. So you can think of even the domain of the system or the situation going from 0 to 12. And so then when you're looking at that, this is the part of the graph we're looking at. And then Desmos, actually this gray circle, the gray circle there is the maximum, and Desmos tells us that the maximum is indeed at 1024. So this is just going a little beyond what the question says. When you get to calculus, you learn how to find the maximum for something like this. In algebra, you learn how to find a maximum for a quadratic, but what do you do when you have a cubic? So calculus will teach you how to find that maximum when you have a cubic. So that's something that you will learn when you move on to the next course. So do you guys have any questions on this example, this word problem? I'm going to add in here that we could say that x has to be between 0 and 12 if we're looking at the situation. Okay, well, I have a lot more. I severely overplanned because I have a lot more slides. 1.4 contains a lot of information. So I'm going to do a two-parter, basically. I'm going to have to look at my calendar tomorrow and see, and we'll do a second session to do the rest of 1.4, because the rest of 1.4 involves the difference quotient, which is also something that comes up in calculus, so I want to make sure that I go through that. So this will be a two-parter. So I'm going to stop here, and then I'll look at my calendar. I will look at our the survey for when you guys are available, and I will try to pick out a second time. It'll probably end up being on Sunday because I have things going on tomorrow night, Friday night, and Saturday night. So Christmas is a very busy time, lots of events. So do you guys have any questions on anything maybe not related to what I've talked about so far? All right, you guys have gotten pretty quiet. Okay, so this recording will probably take a while to process, so I will probably send it out, put it in the classroom and everything tomorrow. I'm also planning on tomorrow making a video on week 1 so that you know more details specifically about what you have to do for the discussion in week 1, what you need to do for the application assignment. If there are things that people usually mess up on the application assignment that you should watch out for, specific details on the journal entry, on the self-assessment. So I'm going to make another video for that. I'll share this one also tomorrow, and then I will also contact you guys when I have figured out when I'm going to do part 2. So thank you guys for showing up and sticking through this whole hour long with me. I really appreciate it. You guys are that's impressive, doing math for an hour, learning math for an hour. So I really appreciate it. So if you guys come up with questions later, feel free to email me or give me a call, or especially if you decide to review this recording after I post it, you can always email me. If you have other examples, you're like, what do I do in this situation? Let me know. So, all right, I'm going to pop off, let this process and all that, and I will hopefully see you guys at my part 2 or talk to you in the discussion forums. Alrighty, you guys have a great evening, okay? Bye.